9, so let's get started. Good morning. So let's look at a couple of problems from worksheet and then we'll continue last time's lecture. So let's look at number 1. Did you guys have any trouble with solving number 1? Have you guys tried number 1? Not yet? So let's look at it, okay? See how you do this. So this is about optical cable or optical fiber. Okay. So let's say you have a long optical fiber that has index of refraction of 1.265. So I'm going to do the problem for a different refractive index and then you guys can work on this one. Okay. So let's say the refractive index is 1.35. Okay, I'm going to use 1.35. So we have this refractive this optical cable. Okay, and you pass the light in the optical cable. It hits the inner part of the optical cable. Usually in the optical cable there is something called cladding. Cladding is kind of a cover that prevents it from damaging. Okay, it also works as a medium to support the total internal reflection. So you have a cladding outside the optical cable, a cover, something like this. Okay, something like that, and it's covered with some kind of transparent medium. But in this problem it says there is no cladding. Okay, instead the outer medium is air, so we don't need to worry about cladding. So our outer medium is air. That means the outer medium has refractive index of 1. Okay, and the refractive index in the optical cable, let's call it NO, is 1.35. Yeah. So now let's draw a normal here. Okay, that's the normal. And if this angle, so again angle is always measured in reference to the normal, so we usually draw dashed line for the normal. So let's draw dashed line for the normal. So I'm going to use dashed line for the normal. Now if this angle of incidence, theta I, or I can call it theta 1, if this is less than critical angle, if theta 1 is less than theta C, then it will be refracted in air. Okay, it would go like that. But we want total internal reflection. Okay, so total internal reflection will occur if our angle of incidence theta I is greater than theta C. So if this angle is greater than critical angle, then instead of going into this medium, it will enter in the same medium. It will reflect back in the same medium. Now, exactly at the critical angle. So suppose this angle is exactly critical angle. Then in that case, it will go through this surface. So let's say, let me choose different color here. So if I hit this inner part of the optical cable exactly at critical angle, okay, so let's say this is theta c, then it will move along this surface. So that's that. Okay. And again, I need to draw arrow to show the path of the light. So it's going from glass to air. Okay. So we want to find critical angle, and then the total internal reflection will occur for any angle that is greater than the critical angle. So the minimum angle at which total internal reflection occurs is slightly greater than the critical angle. So let's find the critical angle. So we can use Snell's law in, let's say this is medium 1 and that's medium 2. Okay, in medium 1, refractive index is, so Snell's law, we have Snell's law. Refractive index in medium 1 times sine of angle in medium 1. So let's say it's theta c, which is the critical angle. But for now, we can just say theta 1. Okay, we'll use theta c later. So let's just say theta 1 in medium 1. And then refractive index in medium 2 is n2. And sine of angle of refraction, or angle in second medium. So in this case, angle in second medium is this one, okay, theta 2. Or for this green one, the angle would be 90 degrees. So for this green one, that's the angle, theta 2. So now let's see what we have here. N1 is the refractive index of the optical fiber or optical cable, which is 1.35. Okay, sine theta 1 is critical angle. Okay, N2 is 1, that's the refractive index in air. And sine, if we are finding this critical angle, then the angle of refraction corresponding to the critical angle would always be 90 degrees. So that would be 90 degrees. Okay, again, by the definition of critical angle is the angle of incidence. Okay, so critical angle is the angle of incidence for which angle of refraction is 90 degrees. That's the definition of critical angle. So now we need to do the math. So let's look at the math. So sine theta c is equal to, sine 90 degrees is 1. 1 times 1 is 1. 1 over 1.35. Okay, so we want to find theta c. Theta c would be sine inverse of 1 over 1.35. And then let's see if I have calculator. No, I don't have calculator. Why don't you guys do that calculation and see what you get? Anyone has answer for that? 47.8. Okay, so that's the critical angle, and the answer for this question would be any angle greater than 40 angle. I should say any angle of incidence. Any angle of incidence that is greater than 47.8 degrees will result in total internal reflection, TIR. So that's how you do the number 1. Okay. Now let's look at number 2. Okay. So in this problem, you are asked to find the depth of the water pool. You can use Snell's law to find the depth, because in order to find the depth, so we have this triangle. If we could somehow find this angle, then we can find this depth, because we have this distance and we have that angle, and using that triangle we can find this distance, which is the depth, required depth. Okay, so we need to find this angle first. So to find this angle we can use Snell's law. So if we use Snell's law on the surface of water, so that's the water surface, and let's draw a normal. So that's the normal. And I'll use dashed line for normal. And we have this incident ray, and we have this refracted ray. Okay. So the light is going from water to air. Now the angle of incidence and angle of refraction are always measured with respect to the normal. That's something you need to always remember. Okay, that's the normal. The angle is always measured with respect to normal. So in this case 14 degrees is with respect to the surface, so we need to write this in terms of the angle of refraction. So this whole thing is 90 degrees. This is 90 degrees, the angle between the surface and the normal. And if we have this to be 14 degrees, then this would be 90 degrees minus 14 degrees, which would be 76 degrees. So this is 76 degrees, and this is something you need to find. So theta r. Okay, and with that we can find that. We can find that. This is what we need to find, and this is given. So this is 5.50 meters. So let's use Snell's law. So this is air, and that's water, NW. So Snell's law here is so I'll do this problem for, let's say, not 14 degrees. Okay, you guys will do this. So I'll do this for 16 degrees, and I'll do this for x is equal to 6 meters. Okay. So let's see, if I use this as 16 degrees, then this would be 74. Okay. I will let you do the problem, but for this one I will use different numbers. So 16 degrees will give me this one 74 degrees, and this one I want to use 6 meters. Okay. So Snell's law is refractive index in water, sine of angle in water, which is theta r, refractive index in air. Sorry, I should write this theta I, because this is the incident, that's the incident ray, so I should write this one to be theta I, or you can write theta 1. It's just using subscripts. So I should write this one, theta I, angle of incidence, refractive index in air, and the sine of theta r. Okay, that's the angle of refraction. So NW is not given, but we need it. Okay, without that we cannot solve this problem. That means you need to find NW from your textbook, somewhere on your textbook, maybe back of your textbook. You can even Google that. So refractive index of water is 1.33. Sine theta I is something we need to find, and Na of water is, refractive index of air is 1, sine 74 degrees. Okay, so sine theta I is sine 74 degrees over 1.33, and then we need to find theta I. Theta I would be sine inverse sine 74 degrees over 1.33. So you can find this quantity first and then take the sine inverse of that and see what you get. So let's do that and see what you get. So tell me a number once you get the answer. Do I have an answer for that?
About 46.3.
Okay, 46.3 degrees. Now look at this triangle. So we have this triangle. Okay, so that's theta I, and that's 6 meters, and this is unknown. So if we use, in this triangle, if we use tan theta would be opposite, which is 6 meter, opposite over the base, okay, which is question mark. So this is the opposite, because our angle is that, so opposite of that is that. So question mark would be 6 over 10, 46.3 degrees, and that will give me my answer. So let's find that out. You guys have answer for that?
$5.3.
5.3 meters. Okay, so that's the depth of the base of the pool. Okay, so that's that. Now let's continue our discussion from last time. We talked about image formed by lenses last time. We saw a bunch of rules to find the image formed by lenses. So today we will do similar kind of discussion for mirror. Okay, so just like lenses, we have two types of mirrors. One is called concave mirror, and the other one is called concave lens. So we have two types of mirrors. Actually, three types of mirrors, I should say. We have plane mirror, which we already saw last time. So it's just a straight plane mirror, okay, smooth straight mirror. So that's the reflecting surface, and this is the non-reflecting surface. So that's reflecting surface. And we also have curved mirror or spherical meter, which we called spherical meter. And there are two types of spherical meters. One is convex, and the other one is concave. Okay. So spherical meter is basically a part of, we can imagine spherical meter to be a part of a sphere. Okay, so imagine that you have a sphere. So you have a sphere, and you take a part of that sphere. Okay, you take a part of that sphere, so if you take the part of that sphere, now it would be a spherical meter. So this is the spherical meter. Now if this part is the reflecting surface, if you consider this part to be the reflecting surface, it's called concave meter. Sorry, not concave, convex meter. So that would be the convex meter. So that's the reflecting surface for convex meter. And if the inner part is the reflecting surface, then that's called concave meter. Okay, so that's inner part reflecting surface is called concave, and outer part reflecting surface is called convex. Concave meter is also called converging meter because it converges the light. So this is also called converging meter. And this is also called diverging meter because it diverges the light rays. Yeah. So in this lesson we will be talking about the spherical meter. Now, like I said before, these meters, concave and convex, are parts of a big sphere. So let's say you have a sphere. Okay. And you know that sphere is characterized by its center, so it has a center. So let's say that's the center of the sphere. Okay, and then it also has radius. Any circle has a radius. So that's the radius. Okay. So that's, and I can draw the same line on this side also. Okay, the same line on this side. So this is center. We use the letter C for that, and this is the optical center. Okay, so this part is our meter. It could be either concave or convex depending on which one is the reflecting surface. So this is the meter, so we call the center of that meter as optical center O. Okay, and the distance between the center of the meter and the center of the sphere from which the meter is extracted is called center of curvature, or radius of curvature. This C is called center of curvature. It's the center of the sphere. That's the center of curvature, and this distance is the radius r, which is called radius of curvature. Okay, and half of that is denoted by letter F, and then that F is again halfway between O and C. F is called focal point. Okay, so FOCAL, focal point. And then the distance between O and F is denoted by small letter f. So that's called focal length. So focal length is f. It's half of r. So r is from O to C, and f is from O to F, where f is, this big F is halfway between O and C. So f is half of r. Okay, so then this would also be f because it's the same distance as the other one. Now I can draw the same kind of, same length on this side also. So I can draw C here. C would be, the distance between C and O would be r. And then halfway between C and O would be F, focal point. And the distance between C and F, or F and O, would be small f. Okay, that's the focal length. So these are some of the properties that we need to know to deal with the meters. These are some of the properties of meters. So for any meter, let me draw the meter again here. So we have a straight line, and we have a meter. Okay, in this case, let's say we have a concave meter. Concave would be this inner part is the reflecting surface. So then this meter is characterized by its center of curvature. So C would be center of curvature, and then this is O, optical center. Halfway between C and O would be F, and the distance between F and C would be small f, which is the focal length, and that's also focal length. Okay. In the same way, we can also draw these quantities for convex meter. We have, let's see, a convex meter. So for convex meter, this one is the reflecting surface. So we'll draw C on this side. You can also draw on this side because it's just the length, and the halfway between O and C is F. That's focal length. That's focal length. Okay, that's what we need to know to see where they form the images. Okay, now let's look at the 3 rules that you need to know to see where they form the images. So let's look at the image formed by a, sorry, that's not lens, that's mirror. That's the concave meter. So this is concave meter. So this is concave meter. So let's look at the rules. So we have the object between C and F. You can place the object anywhere, but depending on where you place the object, you will get the image at different points. Okay, in this case, we are placing the object between center of curvature and the focal point. So the first rule is it's the same as the rule in the lens. If the light from the object hits the mirror parallel to the axis. So we have this axis, principal axis. This is called principal axis. So you have this axis that is passing through the optical center. That axis is also called principal axis. You can just call it axis. So any ray that is parallel to that axis will be reflected. So be careful. In the lens, last time the ray passed through the lens. It was bent by the lens. Okay, so it just passed through the lens. But in this case, the ray would be reflected, not refracted. Okay, because the function of the meter is to reflect, not refract. So it will be reflected back in the same medium, and the ray would be passing through the focal point. So any ray that is parallel to the principal axis will be reflected through the focal point. That's the first rule. Second rule, any ray that goes through the focal point, okay, any ray that goes to the focal point will be reflected parallel to the principal axis. So this would be reflected parallel to the principal axis. That's the second rule. And the third rule, if the ray hits the center of the lens or center of the meter, any ray that hits the optical center or center of the meter will be reflected back with the angle same as this angle. So this angle of incidence. Now any ray that would be reflected back at that point would also have the same angle, because it needs to follow the law of reflection. Okay. And then you need to see where the rays intersect. So you see we have three rays here. This ray, that ray, and this ray. They are all intersecting at the common point. And that point would be the point where the image is formed. Okay, so the image is formed at that point. And how do we know if the image form is inverted or upright? Like I said last time, if it is below the axis, it's inverted. If it is above the axis, it's upright. Now this is below the axis, so it would be inverted. It would be like that. Okay. If it were above the axis, it would be upright. Now, what are the characteristics of this image? So the first characteristic is this is a real image, because it's formed by real intersection of the light rays or reflected rays. What that means is if you place a screen or some kind of paper or something here, the image will be casted on the screen. You will be able to see the image on the screen. Okay? So So the image will be projected on the screen. So that's the real image formed by real intersection. That's the first characteristic of the image. Second one is it's magnified, it's bigger than the object. Okay, second one is that. And the third one is it's inverted. Did I say inverted? Yeah. So it's inverted.
So you know it's magnified if it's further back than the original object?
Yeah.
Okay.
It's also it's formed beyond C and it's magnified. So those are the characteristics of the image formed by the concave meter. Now, if you place the object in different location, then you will get different kinds of image. So for example, let me show you a different case here. Let me place it at or between F and O. So let's see. Let me draw a line here. So concave meter. And let's say that's my F focal point, and same distance would be C. That's C. So I'm going to put my object in between optical center and focal point. So let's place an object anywhere between F and O. Okay, so that's my object. The first rule is if it hits parallel to the principal axis, then it will go through F. Okay, so that's the first one. You need to draw the arrow going that way, and then it's reflected back this way. Now, second one, let's use different color here. If this one hits at the center of the meter, then it will follow the law of reflection. Oops. So this would be reflected back at the angle equal to that angle. So it won't be like that, it should be like that. Okay. So that's my incident light, incident ray, that's reflected ray. And the third one, I cannot draw the third one here because this is in front of F, so I cannot pass the ray through F, so I can only draw two. Now I need to find out where the image is formed. To find the point where the image is formed, I need to see where these reflected rays intersect. Where do you think they will intersect? They will not intersect on this side, right? They will just diverging. No matter how far I go, they will just diverge. So they will never form image on this side. So that means I need to draw the dashed line to see if the image is formed on the back of the meter. So I need to draw dashed line. Where is my? So produce it backwards. And then this one also backwards. And this one a little bit more back. Okay, so I need to draw dashed lines for that. So dash. These are not the real images, I mean real rays. They are just the rays that are produced backward, and they meet somewhere here. So see, Okay, so they meet somewhere here. That means that would be the point where the image is formed. Okay, but this image is not formed by the real intersection. This is formed by the rays that are produced backwards. So when there is no real intersection of the image and the image is formed by producing the rays backwards, then this kind of image is called virtual image. Okay? This is virtual image, not real image. And because this intersection is above the axis, so that means it is upright. In the previous example, it was below the axis, so it was inverted. Now it's upright. And it's highly magnified. You see that, compare the size of the object and image, this is magnified, bigger than the object. And it is formed beyond or behind the meter. Okay, so formed behind the meter. So it depends on where you locate the object. The image is formed at different locations. Now let's look at convex mirror.
Would that one?
Sorry, yes.
Sorry, would that one be magnified still?
Yes, that's the magnified, because
The distance is still bigger.
you just compare the size of the object and image, right? This is the size of the object, and that's the size of the object, right? It's bigger, so magnified. Okay, so let's look at convex meter. And for convex meter, no matter where you place the object, the image is always diminished or smaller than the object. Okay, and it's always virtual. So unlike in the concave meter, you cannot form the image on a screen. It's always formed by producing the reflected rays backwards. So the first rule, the first rule is a ray that hits parallel to the principal axis will not be converged. Okay, this convex lens diverges the rays, not converge. So it will diverge the ray in such a way that the ray would appear to come from focal point. So this diverged ray, this is the diverged ray, and it appears to come from the focal point. First rule. Second rule, if you hit the meter pointing towards the focal point, okay, so you are pointing this ray towards the focal point and you hit the meter at that point. So that ray will be reflected back parallel to the principal axis. So this ray would be reflected back parallel to the principal axis. Now just by looking at the two reflected rays, this is the reflected ray and that's the reflected ray, you can say that they will never meet anywhere on this side. They will never converge on this side. So they are diverging from each other. We can also draw third one. Third one would be, let's see, that one. Okay. So this is the third one. Now this will follow the law of reflection. It will be reflected back at an angle equal to this angle. Okay. So whenever the rays hit at the center, the ray would be reflected back at angle equal to the angle of incidence. So it will have the same angle. So we have three rays, three reflected rays, this one, that one, that one. So you can see the arrow, they are all reflected back. Now they will never meet anywhere on this side. That means there is no actual intersection. There is no real image. So we need to produce the rays backwards. So produce this one backwards, that one backwards, and we also need to produce this one backwards. Okay? So if we do that, let's produce the third one also backwards. They will meet at a common point. So this one, that one, and that one. They are all meeting at that point. Okay? And that point would be the point where the image is formed. Okay? And in this case, the image would be virtual because it's the image formed by producing the light rays back, and it's also upright because it's above the axis. Okay? So that's the image, and you see the size. Compare the size of the object and image. Image is smaller than the object, so it's diminished. Now, like I said before, no matter where you place the object, whether here, or here, or here, or anywhere, you get the same kind of image for convex meter.
So it will always be virtual diminished and upright.
Yes, it's always virtual. So we'll talk about the application of this next time, but before we leave, I want to just mention one thing here. So this may be a formula that you will need to do some problems from worksheet. So instead of drawing this kind of ray diagram, we can sometimes find the location, okay, or the magnification of the image by using this formula. This formula is called thin lens equation or meter equation. It's also called meter equation. If we use this for lenses, it's called thin lens equation. If we use the equation for meter, it's called meter equation. Now, some textbooks use the sign O and I, and some textbooks use S and S prime. Okay? So the meaning of those things are, so let's go to this picture. So S is object distance. Okay, this is object distance. It's the distance between the lens or the meter and the object. So in this case, our object is this one. This is the object. So the distance between O and this object is S. Okay, and S prime is the distance between the image and the center of the meter. So S prime is that distance, image distance, and F is the focal length. Focal length is again distance between F and O. Okay, so this distance is F, focal length. And the relationship between S prime and F is 1 over F is equal to 1 over S plus 1 over S prime. Okay. By using that, you can find either focal length or object distance or image distance. So for example, let's look at this worksheet problem. This is the concave meter with the focal length of 20 centimeters, placed 3 centimeters from 60 centimeter optical center. So where do you think the image will form? So in this problem, you're asked to find the S prime, okay, given F and S. So you are given F and S, object distance and focal length. You are asked to find S prime. So how do you find that? To use this equation, 1 over F equal to 1 over S plus 1 over S prime, and then plug the number here, plug the number there, and then find that. Okay. We'll continue that next time if you still are not sure what I'm talking about. We don't have time right now, so we'll continue this next time.